today Professor Dan Weld from the University of Washington. Professor Weld received his Ph.D. from MIT Artificial Intelligence Lab, and his academic background includes a bachelor in both Computer Science and Biochemistry from Yale. A few weeks ago, I happened to be in Krzysztof's lab, and Krzysztof came into the lab very excited, and he told his students that Dan is coming to Harvard. And one of the students asked, who is Dan? Krzysztof paused for a few moments, and he said, Dan is definitely an AI person. So I loved his definition. It's very precise, because Dan contributed to many subfields under the big umbrella of AI, including model-based reasoning, knowledge representation, machine learning, automated planning, intelligent user interface, human-computer interaction, decision theory, theoretic crowdsourcing, and more. So I think this definition really suits him. In addition, Dan co-founded several successful company, and he holds several patents and technology license. If that is not enough, he is looks like he's a great hiker. You could check out his website. He got beautiful pictures from hiking around the world. It's my honor to present to you Professor Dan Weld.
Thanks, everyone. It's a real pleasure to be here. It's also a little bit intimidating because this is a new talk. I've never given it before, and I was modifying slides late into the night. So I expect it may be rough. So if something doesn't make sense, I hope you guys will please speak up and ask questions, and maybe we can make it interactive. Because I think there's a lot of really interesting issues here that I'm still trying to work out myself. So please, please interrupt me. Uh-oh, that's a bad sign. Yes, you have to stick this thing in here. Okay, so I'm going to talk about socially beneficial AI and challenges. What I'm not going to talk about is stuff that I actually know a lot more about and where most of my research is directed currently. So whether it's intelligent interfaces or machine reading, natural language understanding, information extraction, or especially most recently using decision theoretic techniques to control crowdsourcing workflows. I'm not going to be talking about any of that. So if I speak with you afterwards, I'm happy to talk more. But today what I want to do is focus on sort of high-level AI issues. What I'm going to do is start by telling you some issues I don't think are important, and then I'm going to try to focus on what really is concerning me. One is the sorcerer's apprentice scenario, which I'll get to in a second. Another one is a set of issues and risks about training data. And then finally, some issues, more sort of societal, political issues about deployment of AI systems. And before I do this, I feel like I should say I think AI has huge amounts of promise. And if you look, for example, at transportation, 1.3 million people killed every year in accidents on highways. That's just crazy. So if we can build self-driving cars that have superhuman performance at sensor interpretation, we can really save a large number of lives, and even more, 50 million injuries a year. The potential for benefit is extraordinary. Similarly, just looking at medical accidents in hospitals and healthcare facilities, 250,000 deaths every year just due to making accidents. So if we have AI systems that are double checking what physicians do, huge potential benefits. So there's benefits all over the place. I'm going to take the benefits sort of as self-evident and focus on the risks. So what are some of the risks? Well, one is that AI might destroy the world. So Stephen Hawking thinks it could lead to the end of the human race. That's bad. Bill Gates thinks that we're maybe summoning the demon. That's bad. Stuart Russell is worried that sometimes humans reach a certain level of intelligence, they'll be able to work on AI just like we do and improve their own capabilities, redesign their hardware and so on. The intelligence will zoom off the charts, leading to what Nick Bostrom calls an intelligence explosion. That sounds bad. So the question is, when are humans going to have superhuman performance? And I think the answer is not in 20 years, not in 10 years, but they have it now, right? They have superhuman performance in multiplication. They're much better than I am at spell checking. They last year beat the best human at the game of Go. So there's many, many areas where computers are better than people are today. And that set of skills is going to keep growing over time. But these systems are really idiot savants. So they're really good at one or two small things, but they're not good at everything. And just because they're good at some things doesn't mean they're ever going to be good at everything, or not anytime soon. And so I agree with the AAAI 100-year study panel that the risk is very, very far off to be thinking about these things. And I really think that all of the media attention focusing on intelligence explosions is really a bad thing for the community, because it distracts us from what are so much bigger issues that are going to be coming much sooner. So I don't think that we should be focusing on Skynet. I especially don't think we should be worrying about what Stuart Russell is caring about, that we're going to give our AI systems some goals to achieve and they're going to rewrite their goals. Can we figure out some way to make sure they don't rewrite their goals? That just doesn't seem to me like a problem worth studying. It's the wrong question. It's really unlikely an AI system is going to wake up and decide to kill us, but it's actually quite likely that they will tell it to do something, and they might do something unintended that we didn't expect, and that actually might lead to some serious problems. So let me start talking about what I think the big challenges are. And the first one is the sorcerer's apprentice scenario. And I think everybody knows the sorcerer's apprentice story. I think I will skip past that. We want to make sure we don't give open-ended goals where the system might do it too well. We should be really worried about AI systems that could accidentally hurt us while taking our orders too seriously. And this isn't a problem now, because all of the deployed AI agents pretty much are rote. So when you ask Alexa to do something for you, it's based on a script. There's no real AI search or planning involved. Similarly, if you put a Roomba in your house, it's not actually planning to achieve some goal, it's just doing a set of rote actions. But before too long, we are going to be able to put these planning-based systems in deployment. In fact, Viv Labs has an assistant very much like Siri or Google Now or Alexa, but it does use a planning algorithm. The company was acquired by Samsung, so we may see Samsung phones coming out with assistants that have more capability. And then we get challenges. So once you've got a planner inside your system, then sometimes the planner comes up with a way of achieving your goal in a way you didn't expect. So I might say, okay, Google, how much of my SkyDrive storage is used for my photo collection? And I've got a specific plan in mind when I ask the agent that. I expect them to sort of sum over all of the directories and take the aggregate file size. But there's another plan that one can come up with. I don't know if anybody's figured this one out. We could execute RM star. And then the answer is very obvious. There's no storage being used for your photos. And actually, that's a very nice, simple, elegant plan. So how do we make sure that our AI agents don't come up with that plan? Instead, they come up with the plan that we had in mind that didn't have these harmful side effects. I think that is a key challenge. And so thinking about it, what is the challenge? It's the agent's effectors that cause harm. In the last case, it's the fact that the agent could execute an RM star command as opposed to just purely information gathering commands. So in some sense, there's this multi-dimensional space for thinking about AI agents. On one axis, we've got intelligence, which in some sense is like how much of the search space is the system thinking. On another axis, we've got what kinds of effectors, what kinds of commands can the agent actually execute. And if we give our computer systems these very powerful effectors, then bad things can happen, even if the system's not intelligent. So in contrast, AlphaGo is much more intelligent, and yet it's not going to hurt anybody because it doesn't have any effectors. All it can do is print out on a screen what position it thinks the Go stone should go. So this distinction, I think, is really important, but it's also only part of the story. And in particular, there's this correlation because as we get systems that are more and more intelligent, there's this temptation to give them stronger and stronger effectors. And so I think it's important to keep this distinction straight, but they are linked because of our desire to get more bang out of the intelligence buck. And the intelligence part is especially problematic because it can lead to unpredictable behavior. So I think there's a really key challenge about how we prevent unpredictable things from happening. So thinking about these effectors, we look at what the Roomba can do. It can just sort of drive around our room, vacuuming up a little bit. It really can't do very much harm. In contrast, if we have an agent that has got a bulldozer blade and a big horsepower engine, or it's got a missile launcher as an effector, then that's pretty clearly, obviously dangerous. And there's a really interesting middle ground, which I'm still having trouble thinking about, so I'm not sure if I can get this idea across. But I like talking about effectors that are physically complete. And what I mean by that is it's sort of by analogy to Turing complete computation. So I think if you think about a human hand, right, it can't really do all that much by itself, but with a human hand you can create tools that can create other tools, can create other tools. So if you've got enough time and enough thinking involved, the human hand can create things that are very, very dangerous. So there's this issue about, at a certain point, we may not be putting the missile launcher on the AI agent, but we have to be very careful that we're not giving it the capability to do something unexpected. So I think this idea about physically complete effectors is really interesting, but this is one of these weird points in the talk where I'm not quite sure how to tie this into the rest of the talk. So I hope you'll forgive me if there's a little bit of a disconnect. But I'm still trying to think through this physically complete effector idea. Another really interesting idea is this concept Stuart Russell has popularized, and he's pointed out that no matter what goal you give your agent, there are certain subgoals which are always going to be useful. For example, preserving your own existence is always going to make it more likely that you can achieve a goal like getting the coffee. If you're dead, you can't get the coffee, so we might as well stay alive. Similarly, another subgoal is, gosh, if I had more power, more resources, it's always going to make it so that I can be more effective at getting coffee. So there is this challenge that a system with some sort of unbridled amount of computation might start going down these directions. And if it gets more and more resources and tries to stop being killed, well, that's sort of a dangerous, potentially dangerous combination. So we need to think about ways of preventing these kinds of out-of-control things from happening. I'll come back to that in a second. It's actually pretty challenging. So suppose we wanted to get the next generation Roomba, we call it Roomba ++. And it's got this physically complete effector, two of them, in fact. And you know, obviously, amongst other things, we'd like to have it clean up our house. The question is, what the heck do we tell it to do? So we could tell it, clean up as much dirt as possible. But is that a good idea? What could possibly go wrong? Well, I think one thing it would do is it would start making messes because then it can clean them up, and that lets it increase its utility function. So that's not a good definition. So we could say something like, clean up as many messes as possible, but don't make any yourself. And that sounds good, but if it is able to think pretty carefully, it could come up with another plan, like turning off the light and putting obstacles in front of the door so that when you come home, you trip and make a mess, and it can clean it up, getting more utility. So you could say, forget about that. Just keep the room clean. And the problem with that is the observant robot probably noticed that your cat sheds. And so it could easily keep the house a lot cleaner if it killed the cat. Or maybe it just locks the cat out. And in fact, I track dirt in too, so it's going to keep the house even cleaner if it keeps me out of the house. So that's not so good. So you could say, clean up any messes made by others as quickly as possible. And that sort of works, but it doesn't really work. First of all, it doesn't give an incentive to help you prevent making messes, but also if it saw that it was right next to you, it might want to trip you because then it's going to make a mess. It can clean up so fast that it's going to decrease the average cleaning time and give it more utility. So I think for any definition one can come up with, there's usually some sort of gotcha, and it's really sort of a challenge. Really what you want to say is let's keep the room as clean as possible, but don't do bad things. And that seems like a good idea. Actually harkens back to Asimov's law. 3 laws: a robot shall not harm a human being or through inaction allow a human being to come to harm. In the second law, we have to obey orders unless it violates the first law. This is really sort of getting at exactly what I was saying on the last slide, and it worked really well for Asimov. I don't know, how many people have read his stories? Not as many as I would expect. Well, the rest of you should go out and read them. They're really quite good. And it seems like this is a reasonable solution. In fact, Oren Etzioni and I wrote a paper some years ago proposing exactly this and putting a first law capability into an AI planning system. And the idea is really you're sort of specifying with a set of constraints, a set of harmful behaviors, and now the system can still do its search to figure out what it's going to do subject to not violating these harmful behaviors. But it's not really that great a solution. And the reason why it comes back to this first law, in Asimov's stories, the robots already knew what was harmful, right? And never thought when I was a kid reading those stories, how did they figure out? But harm is a very, very complicated notion. It's very, very hard to define. It involves very complicated trade-offs. And furthermore, it's different for different people. So you can't even have this ANSI standardized definition of harm because, I actually want peanuts on my food, but for some other people, peanuts are poisonous and so on and so on and so on. We all have our own notions about what we don't want the robots to do. So I think the real issue comes down to 2 points. One is, how can a user teach a machine what's harmful? And maybe even more importantly than that, how can we know when the machine understands what's harmful, especially if they're using some sort of deep neural network inside their positronic brain. And that works really well, but how do we actually know what's going on, and when can we be confident that it really got the point? So I think this leads to an area of explainable artificial intelligence. How can we get our systems to explain what it is they're doing, and especially explainable machine learning? How can we have a dialogue with our system to understand best what it's learned about the world? So I really think that this is one of the key problems, and there certainly are some people working on it. I'll describe a little bit of work in just a minute that I think is quite exciting, but I really think it needs a lot more attention. So here's sort of the way the human machine learning loop looks today. We can basically learn a model based on data, and we can look at its accuracy with a set of statistics, and then that usually causes us to go back and change the model to try to make it better, oftentimes with better features, feature engineering, adding more labeled training data, and so on. And we go around this loop a lot. This is what people do, but it's really quite inadequate. So here's an example. Standard machine learning data set is a set of 20 news groups talking about a variety of topics, but one thing is talking about atheism versus Christianity. And you can train on that data set, and a relatively simple logistic regression classifier is going to do phenomenally well with just a bag of words feature representation, and in fact it's going to get 94% accurate. And now maybe you'd want it to be more than 94% accurate, but the question is, can you trust this, this classifier? And in this case, you can't really, unless you look into the innards a little bit. One thing to do is to look at the features. I'm sorry, that's a little bit hard to read, but in fact, what the classifier is actually doing is the key features it's learning are email addresses of the people who posted these messages. And so if you train it on a more recent data set, you get 57% accuracy, which is, as you can tell, is not much better than random chance. So it's a terrible classifier, and it was overfitting in this case. So how do we do better? What we really want to do is come up with explanations that, right, in the case of this classifier, it's actually pretty easy because there's not that many features, and we can just look at, it's using a bag of words representation, we can just look at the key features and we can figure out something's wrong. But that doesn't really work with deep neural networks, where I usually turn that off, and then my wife complains that I haven't turned it off. Let's hope it goes away. Okay. So with deep neural networks, we're learning the internal hidden layers are actually learning features. That's what we all love about deep neural networks, but it's also what the real problem is. You can't figure out what they learned. So what we'd really like to have is an explanation where the humans can understand what's going on. So here's an example of something that's not interpretable, a really complicated network. There's a decision tree which is interpretable, perhaps. You probably can't read it, but it's basically saying sex male is age greater than something or other, so on. And then the second thing we want to do is we want to have the explanation actually has to correspond to reality. So there's a data set, and there you can't see it super well, but there's a curve and explanation. Yeah.
So I guess one of the goals you outlined in the beginning of your talk was to build machines that can outperform us, like say AlphaGo. And I'm wondering if that's sort of in contention with this requirement that it be interpretable, like that humans can easily interpret what's going on, because then sort of ex post we can learn how to play like AlphaGo, and at some level, shouldn't we allow the machine to do things that we can't understand so that it can do things better than we can?
Yeah, I think that's an excellent point. And you're sort of, right, the next point I would like to make is these are the Desiderata, but it's not clear we can actually satisfy both of these Desiderata. It's not clear we can come up with a good model that actually can be explained easily. Or put another way, maybe the model itself is highly accurate, but how do we come up with the best explanation which trades off these two goals? Because in general, to be interpretable, we have to make simplifying assumptions, and that's what makes an explanation easy. If you keep all the details in there, nobody can understand the explanation. On the other hand, then it becomes less faithful, So how do we generate approximations which trade that off? And I think another point that I don't have on the slide is I think it's really important in any explanation facility to have dialogue where a person can ask more questions and get to a more elaborate explanation, or an explanation that looks at a different part of the phenomenon, and that way one doesn't just have to make one global trade-off between interpretability and faithfulness. So I think that that's absolutely at the root of the challenge. Yeah?
I guess the AI doesn't have to give consistent explanations. It can give very simple explanations that are kind of satisfying. They can be inconsistent with each other when you ask it again. So you will be happy, but it basically lies to you.
That's right. Well, that's why faithful is, I think, a desiderata. We don't want it to be lying to us. It should be trying to capture at least as much of the phenomena as it can within a certain level of interpretability. But yeah, I'm 100% worried about that. And I think the European Union is either just passed or is passing laws that certain machine learning systems have to generate an explanation, but it's not at all clear, how you characterize a good explanation or truthful explanation versus one that's lying, basically. So I want to talk a little bit about one technical effort to solve these problems done by graduate student Marco Ribeiro at University of Washington with Carlos Gestrin and Samir Singh. And the basic idea is to figure out, and this is an explanation technique which works with any kind of underlying machine learning system. So it works with deep neural networks, for example. So you could choose a shallow decision tree as your explanation class. And that's not going to be globally faithful, but the question is maybe we can come up with something that's almost as good. And that is to come up with a locally faithful explanation. So here we've got some very complicated decision boundary, and there's no way you can approximate this with a simple, say, linear classifier, but maybe in the context of one particular decision, we can actually come up with an explanation which isn't globally good, but it explains what's going on in the case of this example. That's the idea. It's a locally faithful explanation. And the way LIME works is given a particular prediction, it could be a medical expert system which is recommending a particular treatment. Given the context of that example, it samples a set of points nearby. It uses the complex model, the real, say, the deep neural network, to actually label the sentences for that example, and then it weighs them based on a distance metric, and then it learns a simpler model based on just those examples which are close by, and then it uses the simple model to come up with an explanation. And again, this isn't going to be explaining things globally, but it can lead to explanations that work well and simple in some cases, even with these complicated models. So here's an example explaining Google's neural network for image classification. Basically here, the explanation class is superpixels, so it's basically looking at what pixels are being contributing heavily to the explanation. That's not the detailed model, but that's the explanation model. So for the prediction that there's a guitar in the image, it says these pixels are relevant. For the prediction an acoustical guitar is in the image, it's picking out that. For the prediction that there's a dog in the image, it's picking out the predictions of that. And you can look through this and get a sense about whether you believe that the model is learning things correctly. In this case, it sort of is. And in certain ways it isn't. Here's another example. So you can train a neural network to predict the distinction between wolves and huskies. And in this data set, actually, the neural network did phenomenally well. Only one mistake on the training data there. But should you trust the model? Well, you can use the LIME system to generate an explanation, and it basically if you look at these pixels, what it's actually picking up on is not looking at the dog at all. It's looking at whether there's snow in the picture. So no, we shouldn't be trusting that model. So I don't claim that Lime has solved this whole problem. What I'm really doing is trying to illustrate it as a really promising early effort and as a call to action, because I think that we should be spending a lot more time thinking about these issues. Coming back to the outline, what I want to do now is talk about not so much the AI stuff, but the machine learning, the data on which the AI system is based. And I want to highlight what I think are three really interesting risks. One are dangers that come out of people who might attack an AI system by messing with the training data. There's people who might look at an AI system and then come up with adversarial examples that are designed to fool it. And then there's a question about underlying bias in the data itself. So attached to the training data, I assume everybody is aware of Microsoft's TAE system, which went out and it chatted with people, and pretty soon it was making very nasty racist comments. Why? Is that Microsoft's fault? Well, you can argue about that, but if you look at what happened, people started saying all sorts of racist things to it, and because it had a learning model, it started repeating those things to other people. So if you will, people were trying to corrupt it, and they were very successful, which is why TAE is not online anymore. So this is a pretty clear risk, and I think one has to be very, very careful about putting in adaptive systems that are continuously getting new training data. A different kind of attack, I think, is really even more interesting. So here is a machine learning classifier, and it looks at that picture, and it has a moderately high belief that there's a panda in that picture. It turns out if you add in a little bit of that noise, just a tiny little bit, 0.7% of that noise into this image. And why exactly did I pick that noise pattern? Well, I had access to the neural network parameters. If you add that noise in there, you get that image that you see there. And I think most of you think it still looks like a panda. But the classifier is now 99% sure that it's something very, very different. So this is an example of an adversarial attack, a deliberate attack on the classifier that you can do if you've got access to the neural network parameters. But the big part is actually, in some recent work, it turns out you actually don't need to have access to the neural network parameters. All you need to be able to do, you don't even need to know the neural network structure. All you need to do is be able to make a small number of queries to the neural network, look at its predictions and its confidences, and you can uncover enough to generate that adversarial example. And furthermore, you might think, well, we can get around that by changing the training data. For example, if we're worried about our Tesla car having some susceptibility to artificially generated images that might cause it to swerve off the highway, thinking it sees an exit when in fact there's no exit there, we could try training all of our Teslas on a different subset of the training data so that all of the different neural networks inside each one are different. That way nobody could buy one Tesla, issue some queries on it, and then use that to attack a different one. Unfortunately, it seems as if that doesn't work. The attack is robust to changes in the training data. So anyway, I have no idea what the solution is here. I am encouraged by the fact that if you put a Gaussian filter on that image, it tends to make the problem go away, but this has got the security people quite concerned right now. So I know that there's some recent work that's that has relaxed the assumption about, they still know it's a neural network classifier, but they've relaxed some assumptions about the structure of the classifier, and they're still able to generate these adversarial examples.
They know what the features are.
What?
They know it's like a 100 by 100 pixel image.
Well, they certainly know the characteristics of the input. But I mean, this is a highly evolving area where you sort of need to read archive like every night to find out what the latest thing going on here is. But anyway, I think it's an interesting challenge for people. But actually, I think the biggest challenge is not from deliberate attacks, but instead it's from bias in the data, and especially the concern, because the training data out there reflects our existing biases, and if you train a machine learning system on such data, you might reinforce those in a way that causes even more problems. So here's an example, a recent study. If you do a Google search, I think this is fixed now, but if you do a Google search for black first names, then you're much more likely to get an ad for a criminal records background check than if you search for a Justin or a Daniel or a more commonly white sounding name. And you know, there's some issues with word embeddings too. So word-to-vec is sort of a key technique used in most natural language deep neural network systems. It allows analogical features, reasoning, but it also is features for LSTMs and other kinds of neural models. So what does it do? Well, it says things like man is to king, as woman is to queen, and so on, which sound right, but you know, if you look at man is to computer programmer, you get woman is to homemaker, man is to doctor, woman is to nurse. It's reflecting a whole set of biases in the training corpus that it used, which maybe aren't the ones that we would like to be adopting in our systems. Here's a recent paper. They were able to predict with 90% accuracy just from a picture of the person's face whether or not they were going to be, whether or not they were a criminal. So that's pretty cool. Or is it really? I mean, what exactly is it learning here? And maybe the Chinese judges were much more likely to think people with those scowling faces were guilty, and so that's actually causal, and that's why they got convicted of the crime, whereas these other nicer-looking people managed to get off scot-free. No idea really what's going on in the data, but it is quite concerning if people think that they can predict these things with high accuracy. And like, oh my goodness, is this what we're coming to? How many people saw the Tom Cruise movie Minority Report? Totally awesome movie. So the Department of Pre-Crime is able to predict crimes before they occur, and the police agents go out just in time to prevent the murder from happening. And it all goes pretty well until it predicts that Tom Cruise is going to commit a crime, and that's where the plot gets kind of interesting. So we're using technology like this today, right? North Point licenses some technology that's used by judges. It predicts the chance that a person is going to commit a crime again, and so that's used in the sentencing decision, how long a term to give with a person. So this is an active use. And the only problem is a recent study by ProPublica showed that it's much more likely to have a false positive, predict that somebody is going to commit a crime when in fact they don't commit a crime if the person is black. And that's despite the fact that race is not used as a feature. Instead, there's a bunch of other features which are highly correlated with race, and so presumably that's what's going on. So this created rightfully created a big stir, and it doesn't seem fair at all. But it raises the question, what the heck is fair? So imagine we've got some sort of protected attribute A, and we've got other attributes like criminal record and so on that seem like reasonable things to use. And we're trying to predict Y, whether or not the person's going to commit the crime again, or whether they're going to repay the loan again, or some other question of interest. And what we're able to do is use machine learning to come up with Y prime, which is some function maybe of X, maybe of A, and that's going to be our prediction. So what would fairness be? Well, one thing you could say is y prime should be a function of x. It shouldn't use the protected attribute a, okay? But that sort of fairness through unawareness is clearly not enough, right? Because there's other variables which are correlated. So, in fact, North Point satisfies this fairness through unawareness. Another thing you could ask for is demographic parity. So basically you could say, I want the prediction to be completely uncorrelated with the protected attribute. But this is, first of all, it's insufficient because it might be 100% accurate at predicting whether a white person is going to commit a crime, but on a black individual, maybe because there wasn't enough training data, it could just have a completely random prediction as long as the percentage with which it predicted black criminals was the same. So that wouldn't be fair to the black people who weren't risks. But furthermore, this demographic parity, it rules out using the ideal prediction. It seems pretty clear that if you can, with 100% probability, predict whether somebody's going to commit a crime or not, that should be a reasonable thing to use. But in this case, it doesn't satisfy that test as long as if there's any correlation at all. So recently there's been some other ideas. One is this idea of calibration within groups that was put up by John Kleinberg and so on. And the basic argument here is what we would like to have is have the true class be independent of the protected attribute given the prediction. And that's a good thing because if that's the case, then there's really no incentive for the judge to ask about whether the person is white or black. Whereas if this isn't conditionally independent, then we're treating those two different classes separately. And so it may be that the white class really is much more likely, after the prediction, is much more likely to really be a criminal. And the judge would want to actually know about this. So this calibration within groups, the fact that the classifier should perform equally within groups, seems like an important criteria. Another criteria is equalized odds, and it basically says we want the prediction to be conditionally independent of the attribute given the true class. And it basically says we want to have the same ratio of false positives and negatives in the two classes. That also seems like a pretty natural criterion. That's the one that North Point was violating. And the problem is that you can't achieve both of these at the same time. So unless you either got 100% perfect predictor or else there is true independence in the classes, you can't achieve both of these. So that's a recent paper. Another recent result is what we can do at least is guarantee equal odds. So given any predictor, any machine learning output that is derived from whatever algorithm, there's a post-processing step that lets us create a new predictor that satisfies equal odds. And in fact, it's Bayes optimal in the sense that it's the best possible, most accurate classifier that satisfies equal odds. And so what this really is, and this is again another paper available on arXiv, is it's kind of a computational affirmative action. It's a way of taking any classifier and making it fair, but it does require using the protected attribute to do so. I'm not sure exactly what the right criteria are, but I think that we need to be involved in these kinds of decisions. And it's really important for us to get this right because if you've got biased data, you've got machine learning building some sort of automated policy that can reinforce the bias. But again, if I think this may have been fixed, but if you go to Google image search and you search for physicist, like 95% of the pictures that come up are of white males. So, what's that going to do to women who are interested in studying physics? Maybe they're going to think it's not for them, and that's going to create a feedback cycle. And of course, in the criminal system, you can see feedback cycles arising as well. So I think we really need to get this right. There's also questions about whether an AI system should explain itself, and I think it should. Brings back to what I talked about earlier and the difficulty in making sure these explanations are right. And then finally, there's some really fascinating issues about liability. who should be responsible for these problems? In the case of Microsoft Tay, was it Microsoft's problem, or is it the people who tricked the system into behaving in a racist fashion and doing hate speech? If you look at today's legal code, it's really pretty inadequate for answering these questions. So some of the issues that come up, depending on what part of law you look at, is whether there was criminal intent behind the action. Well, obviously an AI system probably doesn't have any intent. And whether there was negligence involved. But in a complicated AI system with a deep neural network in there, negligence is based on was the person able to reasonably foresee what was going to happen? If it's an incredibly complicated system, nobody can really foresee what's going to happen. So I think it's easy to argue that there was no negligence. So what this leads to is what Rylan Calo calls deploying AI and creating criminal acts where there's no perpetrator. And that's kind of an interesting conundrum for the legal community. Here's another great example. So Stephen Colbert wrote a Twitter bot which algorithmically took movie reviews off of Rotten Tomatoes and it substituted in people from Fox News. And created things like TV show's most compelling element of all is Palin wandering the nighttime streets trying to find her lover. Or another one that got people quite upset. So is this libellous? It's not clear. It's algorithmic. So how can it be libellous? And again, as we deploy the AI systems, I think it's really important, and there's a complicated user interface question about how do we actually convey the limitations of the AI system to people. There's been a lot of talk about whether drivers know what the Tesla is going to do. A lot less attention to the fact that many cars now have adaptive cruise control. That's where you set cruise control on the highway, and if it sees another car in the lane in front of you, it'll automatically slow down. You don't have to put the brakes on yourself. You move into the other lane, no car in front, and it speeds up. This is quite common, but there's a whole set of limitations. If you come up on a parked car, it won't stop in time, depending on what speed you're going to. So this doesn't, like, exactly when does this system work, when doesn't it work? How do we communicate that to drivers? Even with things like a Google Translate, how do we communicate that the translation may not be very good. You shouldn't use it for a corporate contract or something. It's incredibly hard to predict what is going to happen with AI technology because most technologies follow this exponential curve of adoption. And in fact, looking at more recent technologies, the slope of that exponential curve is steepening greatly. So if we think about these techniques, even technologies that have lots of benefits, if they get deployed much faster than we expect, it raises all sorts of other social issues. Unemployment being a key one. I am bothered, again, that people are talking about AI systems that are creating Skynet, and they're not talking so much about some of these social issues which are going to come upon us right away. I don't think we're going to retrain all of these people to be programmers. So what are we going to do? I sort of regret this slide about inequity because I actually don't think inequity is the issue. I think poverty is the issue. And personally, I think I'm okay with some people being fabulously rich as long as everybody has some sort of basic healthcare, education, and so on. Pretty interesting. I don't know if people saw in the New York Times yesterday, there's some beta tests of universal income in Kenya and reasons for optimism that maybe that's a good solution. But I don't know it's a good solution, but it seems like something we should be talking about more. Okay, so let me conclude. I think the concerns I'd really like people to think more about are things about the sorcerer's apprentice scenario and ways that we can actually understand what our machine learning systems have really learned and what they're doing, as well as a focus on data out there that the learning systems are based on, whether people are attacking it or whether it just has implicit bias. And that's it. Let me end by thanking the Future of Life Institute, which has funded a grant that's using a deep neural network. And at the same time, it's also learning to caption images. And as a result, you can go back and you can ask about the classification decision, and it picks up words. So you ask about, why did you think this was a white egret? And it says, because the bill was long and the plumage is such and such, that it's picked out from the classification system. So it's actually able to put words onto some of those internal hidden features. I think totally cool work. Obviously, lots more needs to be done, but I think that's really exciting. Yeah.
I was going to ask about the start of your talk when you talked about harm. I'm just curious, do you think that, so first of all, what are people doing about that? And secondly, concretely, what if we somehow imagined observing and learning and saying, okay, here's an envelope of actions that I see this person is able to take, and we somehow restrict the planner to act within the action envelope? Obviously we're kind of used to thinking about trying to learn reward functions through observation, and I thought less about trying to learn to think about what are appropriate actions or behaviors or inappropriate actions or behaviors, and somehow trying to put the planner in that box. I'm curious if you want to reflect on that as kind of a way to begin to constrain what harm might mean. How far might that take us? It strikes me that it may be helpful if we think that harm largely occurs when we positively take an action, but clearly harm can also occur if we don't take an action. Like, I should have caught the falling baby and I didn't, right? And just because I've never seen anybody do that doesn't mean I shouldn't do it. So are people working on this problem, and if so, what kinds of approaches?
Yeah, so I think that's a great idea, and I actually don't know of anybody who's working on it, but I think it's very promising. So I have thought about trying to do something that I think is similar to what you're saying, but haven't gotten all that far. The basic idea is basically having some sort of model, in addition to a predictive model, or maybe something that's used by the reinforcement learning system, have a model of what typical actions, typical plans are for this goal. And then when the agent comes up with some especially clever way of achieving the goal that's different from what it's seen before, that seems like it's a great place for it to ask a question and say, does this seem like an okay thing to do? And I think we don't want it to prevent it from being clever, because that's where the potential wins are, but that's a good place for it to have a dialogue and actually double check its work. Yep.
So in lieu of your example about the peanuts, where they're good for some, poison for others, how does, has anybody done any work on how do you make a decision? Because what's good for you is not good for me, or what's positive. Somebody has to at some point adjudicate the decision, and even the Supreme Court, when they were adjudicating what's pornography, they couldn't really define it well enough for the neural nets to take over. That's the first question. The second question I have about the Band-Aid. It's not a general solution, but for very small temporary time, why can't you question the net as saying, are you doing this function for the very first time, and then actually give a decision, if it is the first time, give a decision to a human. Just like, when you're trying to erase some files on your computer and it's asking you, are you sure?
So picking the second question, because I don't really have a good answer for the first question. So I'll go to the second question. I think that's good, and I think that also matches the previous question a little bit. It's challenging. So when is something, when are you doing something? Everything is sort of the first time to some extent, so it relies on some similarity metric about what's important about this scenario, what's different about what I'm doing this time. And so that's sort of a commonsensical thing, and that I think is at the core challenge, that what we need to do is put in some sort of common sense about what's harmful and what's not harmful, what's similar and what's novel and different, and needs to have a dialogue. So I think that's exactly the direction to go, but I think it's also challenging to get there. You have to ask the first question again.
So as you mentioned that some things are poison for some and wonderful for others, on just about everything with I'll use your last example that you gave. You believe that some people should get whatever they get, and there should be some minimal whatever health care. I bet you there is not two people in this room who will agree what's a minimal.
Yeah, so I have, I think it seems pretty natural for different organizations, standards bodies, if you will, to come up with different definitions of harm. And you can imagine other organizations, a religious body coming up with their definition of harm, and then you can choose to adopt some of those, or maybe very quickly when you're breaking in your robot, you can tell it and it'll be able to learn in the context of those known harm models. I think that's one way of, because I mean, certainly you want to ship the robot with some predefined notion of what's harmful and not, but I think there's always going to be customization. So one thing to me that looks like trash that should get picked up off the floor and thrown away, to somebody else that's going to be a valuable something or other. And I don't think there's any magic bullets there, right? We actually have a house cleaner that comes into our house, and we just had to switch over to a new person, and I came home as a disaster. They threw away all sorts of things that I didn't want them to throw away. And I have a conversation with them, and hopefully next time they do better. I think it's going to be, there's definitely going to be some of that with our bots as well, hopefully before the stakes get too high.
I guess my real question is, if even Supreme Court cannot define well enough, let's say pornography, for it, in order to be coded in a neural net.
Well, actually, I don't know. I'm sure somebody must be working on this, but I suspect that neural nets actually do a pretty good job on recognizing pornography. I don't think that they can. I mean, the challenge with pornography is describing what it is in a clear-cut way, and so I don't think they'll be able to do that, but I suspect that they can identify it reasonably accurately. But the explanations are important too. Well, you first.
I just thought it was worth mentioning with regard to the imposition of our own implicit biases on these AI technologies. I think it's worth revisiting the slide with the graphic of the Roomba robot that's sexualized and feminized, because I think that the conflation of domesticity and femininity and female sexuality is a really it's a very salient instance of that implicit bias at work.
It absolutely is, and I must admit I felt badly putting that picture in there, but I wasn't able to come up with a better robot housekeeper picture given the time constraints of putting together this talk. And so I felt badly about it, but probably should have felt even more badly about it to the point of actually fixing it. So my apologies about that, but it does raise that issue. Yep.
Yes. My question was, because we are working with children and digital citizenship, and now with AI, a lot of questions are emerging for us. And one of the topics that we are very interested in is in explainability for youth and children. So my question is, who are the people we should put to talk to design really good explanations for children and youth on AI?
Wow, that's a great question, and not one I really have an answer to. So I think that we don't really know how to come up with any explanations, let alone any good explanations yet, let alone coming up with ones that are especially suitable for youth. So I think that's an interesting question, but I don't really have any good ideas, I'm afraid. It'd be fun to brainstorm about it, but I don't really know. Okay, well, great. I'm around for the rest of the afternoon and look forward to talking with some of you. Thanks.